It's my great pleasure to present our today's speaker, Professor Zalina Kusraeva. This last seminar for this year. Thank you, Zalina, for agreeing deliver a talk at our seminar. Please go ahead. Thank you.
Thank you. Good evening, dear colleagues. First of all, let me thank Professor Karapetyants for giving me an opportunity to deliver the last talk in this year, in 2024. It's a great pleasure and honor for me to be the closing lecturer here today. Also, I want to thank Tatiana for helping with all the organizing stuff. It's a great work. And let me proceed. During this year, the passing year, one of the problems with which I was dealing was about the extreme structure of cones and of positive cones and convex sets of the space of homogeneous polynomials. In other words, this is the problem of approximation of or extreme structure problem, one can say. Extreme structure of cones and convex sets in vector spaces or Banach spaces is one of the traditional topics of functional analysis. And I'm going to speak, as I told, about the extreme structure of convex sets and cones of such a class of nonlinear operators, which is called homogeneous polynomials. And first, I'll give some necessary definitions, and after that, I'll speak about two groups of results in this direction. And the first will be the Crane-Midman type theorem for homogeneous polynomials, and the other group of results which I'm going to present today here is the version of the Klee type theorem, the version of Klee theorem or Klee type theorem for homogeneous polynomials, and also for a special class of homogeneous polynomials, namely orthogonally additive polynomials. So let us proceed. And okay, let us proceed. And I'll start with some basic notions. First of all, it is a convex set. We call a non-empty subset of a real vector space convex if and only if it, together with any two arbitrary points or vectors, it contains the entire interval during these points. A convex hull of an arbitrary subset A of a real vector space is the smallest with respect to inclusion convex set that includes A. In other words, the convex hull of a subspace A consists of all convex combinations of the elements of this subspace. And as we are going to talk about the extreme structure, of course, we'll need a definition of an extreme point. And an arbitrary vector x in a convex set C is called extreme point if it is not the inner point of any line segment in this convex set C. The space of convex sets is denoted by this symbol xc, and here in the picture you can see several examples, not difficult examples of extreme points. In the first and the third case, it is clear that the extreme points are the vertices, and in the case when actually these are unit balls, yes, in L2 space, and in the case when the unit ball is a circle, then the whole boundary is the extreme, it consists of extreme points. There are several equivalent definitions of extreme points, such as, for example, there is an interesting definition given by Klee, saying that the point is extreme for a given subset C. If we extract this point from the subset, then it remains convex again. In 1940, a fundamental result was proved by Crane and Millman. They obtained the following. The description of a convex compact set by means of its extreme points. And more precisely, this means that they proved the following. A compact convex subset of a Hausdorff locally convex topological vector space coincides with the closed convex hull of its extreme points. Here, the compactness of C means that, as usual, from its covering by open sets, one can extract finite subcovering. By this symbol, we this one, yeah. By these symbols, we denote the topological closure of the convex hull, and this result is a very useful result. But it turns out that the compactness condition is rather problematic, and it often happens that we have a kind of compact sets, but not fully compact. For example, these are locally compact sets. This notion is based on compactness, but is not the same. You can see the definition on the screen. More precisely, a subset C of a vector space X is called locally compact if every point of C has a compact neighborhood. And here a natural question arises. Does the Crane-Millman theorem works in the situation when the convex set under consideration is not compact, but is locally compact? In this situation, it turns out that it's not enough to use the extreme points to describe this set, and one has to use extreme so-called extreme rays. And before formulating the result, let me give the definition of an extreme ray. Here it is on the screen. Let me just say that let C be a convex set in vector space X, and an extreme ray C is an open half-line rho in C, such that any line segment joining 2 points X and Y in C lies entirely on a half-line rho, provided that there is at least one inner point in segment XY lying on rho. The set of all extreme rays is denoted by symbol XC, extra C, and from the illustration below, one can clearly see that the convex combination of extreme points of the subset C is not enough to describe it, because the convex hull of these 3 points is obviously triangle, which clearly is not enough to describe C. It does not coincide with it. And in 1958, Klee proved that the following. He proved that a closed convex locally compact subset of a Hausdorff locally convex topological vector space, which does not contain straight lines, coincides with closure of the convex hull of union of extreme points of C and its extreme rays. In other words, this means that each point of C can be approximated by the convex combination of points which are either extreme points, or they lie on extreme rays, and this is illustrated here on the screen below. And starting from this moment, an increasing interest was paid to the following question. What can be said in the situation when the convex set C consists of linear operators acting between Banach spaces X and Y? And more precisely, this problem can be divided into two problems, so-called existence and description problem and recovery problem. And first, which I said is called extreme existence problem, asks the following: under which additional conditions a convex set of operators has extreme points, and what is their analytical representation? And the recovery problem asks, how can be this set recovered from its extreme points or extreme rays? So this is the question. As I said, the interest in this direction was raised starting from 1960s. It was initiated by works of Phelps with his pupils and followers and colleagues. Here are only several works in this direction listed. Phelps, with his co-authors, investigated some special cases, and maybe one should say the following remark. Maybe it should be mentioned that to attack the existence problem, one can try to find a locally convex topology on the space of operators acting from X to Y, under which the appropriate convex set is compact. And an application of Crane-Millman's theorem then yields desired extreme points. But the reason this approach does not immediately yield the desired result is, of course, the fact that the closed convex sets of operators are compact only in very special cases. And one possibility arises if the space of operators under consideration admits a good analytical representation. As I said, Phelps with his colleagues, they investigated very special cases, and next, let me show one typical result, which was obtained by Phelps and Morris in 1970. They proved the following. They proved that the Crane-Millman type theorem holds for the unit ball of the space of linear operators acting from where? Acting from a Banach space X to the space of, let me show the bullet, the second bullet, to the space of continuous real functions on the compact Hausdorff space K. And this is that the unit ball is the pointwise norm closure of the set of its extreme points whenever this K is a special compact space, namely K is totally disconnected. This is the condition. So, in comparison with the classical Crane-Millman theorem, here the operator convex set and operator convex hull are used instead of a convex set and convex hull. But let me define them a little bit later. Next 30 years, there were obtained numerous results about, first, explicit description of extreme points of different convex sets of linear operators, and Crane-Millman type theorems. Here are listed only several, again, not all results in these directions. And let me note that despite of the fact that plenty results were obtained, the most general results were obtained in the last two listed papers by Professor Kutateladze, and they were obtained for the case when linear operators are acting between Banach lattices. And as far as I know, this problem was never investigated for such a nonlinear class of operators, namely homogeneous polynomials. So my task, my problem was to obtain the generalization of Crane-Milman type theorem from linear operators, which was obtained by Professor Kutateladze, linear operators acting between Banach lattices, to the case when we work with homogeneous polynomials acting in Banach lattices. So I think that here it is necessary to give the definition of Banach lattice. It is necessary to formulate the results, of course, and as a precise definition is given here on the screen. Let me just say only that a vector lattice is a vector space which is endowed with the notion of order, where for each pair of elements there exists a supremum and infimum. And a Banach lattice is a Banach space that is simultaneously vector lattice with order relation which is connected with the norm by monotonicity condition. All classical Banach spaces are Banach lattices, with ordering introduced pointwise in the case when we talk about the space of functions, and with ordering introduced coordinate-wise when we speak about sequence spaces. Also I have to emphasize that all the results I am going to present next are obtained for Banach lattices, but to simplify the understanding and without loss of generality, one can keep in mind a kind of LP space over measure space. Each time it can be done each time when I consider an operator acting between Banach lattices. This is not can be skipped. Several definitions will be needed here. These are the notion of absolute value or modulus of a vector of a point in a vector lattice, which is the supremum of x and minus x. Also, we call a positive. We will need a notion of a positive cone in a vector lattice, which is defined as you can see it here. It consists of all positive elements. And the notion of the order boundedness, we say that the set B is order bounded in a vector lattice E if it is contained in an order interval. Order interval is this guy. Okay. Now we also need to introduce the class of nonlinear operators, which I promised to speak about, the class which is under my consideration, homogeneous polynomials. These are the mappings between arbitrary Banach spaces, which can be defined as the as a composition of a multilinear operator with a diagonal operator. And this multilinear operator is called generating. And in the case when, maybe it will be better to say that homogeneous polynomial or polynomial of degree n can be defined as a restriction to the diagonal of this multilinear, of arbitrary multilinear operator, and which is called generating. And in the case when the generating multilinear operator is symmetric, it is unique for given polynomial and is called associated, and is denoted by this symbol p check. A polynomial also, we need the following definition. A polynomial is called positive whenever positive is its associated operator, which means the following. And we denote the space of n homogeneous polynomials acting from x to f by this symbol. and the cone of positive polynomials we define by this symbol. Also, for better understanding of the notion of polynomial, I'll give this example. Let the target space be, as we agreed before, exactly a function space. Let it be L0, it can be LP space, doesn't matter. Let us construct a mapping by the following way. We take a linear operator T from X to L0, and we build a new operator by taking each vector X from X and taking the value of each vector X, value of T on each vector X, and we raise it to the degree n. So constructed operator is an n-homogeneous polynomial as its associated multilinear operator is written explicitly according to the definition. And one can easily check it if we take all the arguments equal to each other. To formulate the result, I will also need the notion of Dedekind completeness. Dedekind complete vector lattice, or how it is called often in Russian literature, Kantorovich space, or the most general is K space. So this notion we call a vector lattice in which for a given non-empty order bounded subspace there exists supremum and infimum. An arbitrary set omega from the space of n-homogeneous polynomials is said to be pointwise order bounded if the set of values of operator P from omega at point X is order bounded in F. And we call it pointwise order closed or O closed if for every net Pi in omega and for every polynomial P from the fact that this set converges or converges to Px, for it follows that P is in omega. And what I promised before, we need to show here the notions of operator convex convexness and operator convex hull. You can see them in the screen, and here we need to say that an operator convex set and operator convex hull are defined almost the same with the notions of convex sets and convex hulls, with the difference that in operator case we substitute the real coefficients with the multiplication operators. The precise definitions, as I said, are here on the screen. Let me not stop here. And finally, now we are ready to formulate the first main result. This is Crane-Midman's type theorem for homogeneous polynomials, according to which a pointwise order-bounded operator convex and pointwise order closed subset of the space of homogeneous polynomials acting from an arbitrary vector space to a Dedekind complete vector lattice can be recovered by the pointwise closure of the operator convex hull of extreme points of its set. This set. So this result was published in the beginning of this year in Journal of Mathematical Analysis and Applications, and I want to emphasize that in the case when n is equal, the power of polynomial is equal to 1, this case was proved by Professor Kutateladze in 1982 in the manuscript which was listed a little bit earlier. So this is the Crane-Millman's type theorem for homogeneous polynomials, and here another question was raised. Similarly with the classical Crane-Millman's type theorem, Crane-Millman's theorem, where we substituted the compactness with local compactness, and the question is, what will happen if we omit the condition of pointwise order boundedness? Will this theorem still be true? And obviously, in this case, Crane-Millman theorem type, this type of Crane-Millman theorem will not be true in this form again, like in classical variant, but there will be two more results which I'm going to present here. These two results, one of these results, obtained results, is for a special class of homogeneous polynomials, namely for orthogonally additive polynomials. And let me define this class. We call homogeneous polynomials orthogonally additive when the additivity condition is fulfilled for any pair of disjoint elements. To clarify this notion a little bit maybe better, let me remind you that we said that each time when we speak about vector lattices, we keep in mind functional vector spaces. So one can say that the polynomial is orthogonally additive when we take two functions which are which have the following properties, that their supports do not intersect, or they intersect on a set with a measure equal to 0. So these are orthogonal additive polynomials. They are the class of orthogonally additive and homogeneous polynomials is denoted by this symbol. And the ordering here is introduced quite naturally. One polynomial is greater greater or equal to another if the difference is positive polynomial, several more definitions should be announced here. This is the definition of lattice homomorphism. This notion is defined as a linear operator between Banach lattices, which preserves lattice operations. Here in this definition presented, we can see one concrete operation of preserving absolute value, but as I said, in definition, all lattice operations are preserved by lattice homomorphism. This definition is rather easy to be written, but not very clear to be understood in this form, in this way. So let me give a typical example of lattice homomorphism. This is a so-called weighted shift operator, which is defined as follows. If E and F are spaces of measurable functions, then one can construct a function by this function by the following way. We take a measurable function phi from omega 2 to omega 1 and a measurable function v, w in F. Then operator T sends any function x into the composite function of x and phi multiplied by w, where and here W is called weight and phi is the shift. So we can think of lattice homomorphisms as weighted shift operators. Also several notations will be needed, and I'll introduce them here. By this symbol VHEF, we denote the space of all lattice homomorphisms acting from E to F. By E tilde, we denote the space of all regular real-valued functions defined on E. And by L tilde, we denote the space of all regular linear operators from E to F. And now we are ready to formulate the result. Let me open all the bullets and start from maybe let me first say that this result, which I'm going to present right now, is the type of Klee theorem for homogeneous polynomials, saying that the three following conditions are equivalent. And let us start from the third condition, which states that the cone of n homogeneous positive orthogonally additive polynomials acting from E to F can be recovered from the set of powers of lattice homomorphisms by means of convex hull and the pointwise order closure taking. Here by order closure, I mean the closure with respect to almost everywhere convergence. The same is true for real valued polynomials. This is the second condition of this theorem. And the first condition means of the theorem means that the cone of positive linear functionals on the power of vector lattice E can be recovered from its extreme rays. Here I'm omitting the definition, the notion of the power of a vector lattice, because it is quite technical notion and is in general is defined as axiomatically. Here I only give the definition of a power of a vector lattice when again we work with the functional vector lattice. So this result was obtained in the second half of 2024 and is submitted again to Journal of Mathematical Analysis and Applications. Also, I want to emphasize, by the way, that in the case when n is equal to 1, we come to a linear case, which was proved by Professor Anthony Wikstedt. Let me show it here on the screen, which was proved by Professor Anthony Wikstedt in 1981. Here he found the conditions for recovering of the cone of positive linear operators. And now let me let me say the following, that let me go back to the formulation of the theorem. Here it is, yeah. And let me say that here the third equivalence condition from this theorem states that if the polynomial under consideration is not orthogonally additive, then it cannot be approximated by polynomials of the form as sums of powers of lattice homomorphisms. And indeed, in this case, the sum of powers of lattice homomorphisms is an orthogonally additive polynomial, and hence the pointwise order limit of any net of such polynomials is also orthogonally additive. So again, here a natural question arises: which elementary polynomials should be taken instead of sums of powers of lattice homomorphisms to approximate an arbitrary polynomial? And the answer the answer is the product of powers. Let me show it to you. Here it is, the product of powers of linear operators, which are in addition lattice homomorphisms. And I'll give the corresponding definition. Given new linear operators acting from E to F, we define a new mapping Q, the red one, okay, the red formula. This Q is an n-homogeneous polynomial which is generated by Q check, which is defined as you can see it here in the slide, and it is easy to ensure that this Q check is the generating multilinear operator for a given Q. One just has to take all arguments equal to X. So one more lemma is true. I should say about it. It says that this class of polynomials is strictly broader than the class of powers of lattice homomorphisms, and more precisely, the polynomial Q is orthogonally additive if and only if Q can be represented as the power of lattice homomorphisms multiplied by some multiplicator gamma. Here the third main result, which deals with necessary and sufficient conditions under which the red formula holds. That is, the cone of positive and homogeneous polynomials coincides with order closure of operator convex hull of the product of powers of lattice homomorphisms. The precise statement tells us that the following three conditions are equivalent. Let me open them all. The first of these conditions tells us that the cone of positive functionals on a vector lattice E is weakly closed convex hull of its extreme rays. The second condition tells us that the same is true for the cone of real valued and homogeneous polynomials. And the third condition was just announced. So this is the third main result, and as you see, we presented three theorems, which are the generalization. First was the generalization of Crane-Millman theorem for homogeneous polynomials, and the second and third result presented here is the generalization of Klee's theorem for, first of all, it was for homogeneous polynomials, and the third result was the generalization of Klee's theorem for a special class of homogeneous polynomials, namely orthogonally additive polynomials. And what I think I will do next is to obtain the analog of so-called Asimov theorem, which was proved by him in 1969, where he obtains that a well-kept convex closed set in a locally convex space is a convex closure of a set of its extreme points and rays. And if I obtain the generalization of this theorem for homogeneous polynomials, it will generalize all the mentioned results in this talk. It will generalize Crane-Millman's type theorem and Klee's type theorem for homogeneous polynomials. So I guess this is all. Thank you for attention. And as far as we are having our seminar session exactly after the Christmas, and I'm sure that most people here in the audience were celebrating it yesterday. Let me congratulate you all with Christmas and wish you happiness, health, and to be blessed not only in Christmas Day, but the whole year. Thank you.
Thank you, Zalina, very much. When we have time for questions, so please, if there are questions, please go ahead, or you can raise hands. Maybe, meanwhile, I ask just a general wondering, and maybe not a precise question, but just a wondering. Since you are speaking about homogeneous polynomials,
Okay.
I have in mind spherical harmonics, which is kind of extension of homogeneous polynomials. Can this technique be applied to the structure of spherical harmonics?
Okay.
Or maybe just to a part of this space consisted of finite sums of spherical polynomials.
Alexey Nikolaevich, I think right now I'm not sure that I can answer you good for this question, because I have first to understand what is the point which you are talking about. I mean,
yeah, I
maybe
understand. This is just that's why
yeah.
I said that it's just a general wondering, maybe just not immediate question. I mean, just if you're on a sphere and you consider spherical harmonics, which can be treated as polynomials if you.
I see what you're saying. Yeah.
So
But
maybe
I have to
maybe
think. Yeah.
yes,
Okay.
of course.
Thank you.
Just maybe kind of new direction, maybe. Okay. So more questions, please.
If no questions, may I say something a little?
Please go ahead.
Okay. I just see Professor Christopher Boyd here in audience, here in the list of participants. Professor, if you can hear me, I want to thank you for your work, for your papers with Professor Snigireva and Professor Rian, exactly about lattice homomorphisms. This was a very good motivation for some of my research. I just wanted to use this opportunity to say thank you, if you can hear me.
Yeah, thank you.
Perfect. It's nice to see new friends, new people on the seminar, and old friends. And I also want to congratulate everyone give to everyone season greetings. Vladislav Kravchenko also, he's traveling now, so he couldn't connect because he just in some way. So, but he sends his warm regards to everyone, every participant of our seminar. So we are happy together with Vladislav, together with our participants and speakers. We are happy to have such a great team of speakers, such nice speakers, very nice talks were during this year, and very nice audience. Well, again, warm greetings, warm season greetings. Let's thank speaker for very nice presentation. Thank you, Zalina.
Thank you. Thank you.
Well, thanks to everyone again, and of course, see you next year. Keep in touch.